No? Okay, so then we're back on track, I hope. And let's start to talk a little bit about medium access here. And then let's build this up from the simplest possible case, that we have one medium and two nodes that wants to share that, just to get a feeling for what are the main problems here. Okay, so here. So this is a very, very simple example where we have exactly two nodes sharing one physical medium. And we can think of this for the purpose of discussion here, we can think of the medium as being a piece of cable, right? Coaxial cable, if you like. Then this would be classical Ethernet. And then we have communicating devices attached to this medium. And in different types of layering structures, one calls the transmitters and receivers different things. In this part of the course, these are called stations, or STA for short. So a station is a node, it's a host, something like a computer maybe, if you like. So this is a device that wants to communicate with some other device here. And they are sharing a medium to do that, a piece of cable here. So how are they going to do that? Well, they're physically separated first of all, and then the time it takes for a signal to go from this part to from that point to this point depends on the distance, the physical length of the cable. And then there is a certain propagation speed of the signal in the cable. So let's think of that as speed of light, or maybe 2/3 of the speed of light, a little bit less than the speed of light. So there is a propagation time here, which is d divided by the propagation speed in the medium. Okay, and why is this a problem, this propagation time? Well, essentially, and here, this is really the main crux with everything, that whatever station 1 decides to do is unknown to station 2 until at least the propagation time has passed after this event. So if something happens here, it cannot possibly be known by this station until t-prop seconds have passed, right? Because the speed of light is limited or absolute. It cannot go faster than the speed of light. Okay, so in a way, medium access is a sort of like it's a game in time and space. Okay, so just to illustrate what's going on here, so let's draw a very simple time-space diagram here. Now we know space is in 3 dimensions, right? And time then it becomes a 4-dimensional thing that I would like to draw here. So I'm going to simplify and say that space is only in 1 dimension. So we have 1 dimension here, space, and then we have time. Okay. So this is the universe we live in right now. It's a 1-dimensional universe in its space coordinates, but we also have time. So if something happens here at some point, an event, say event number 1 here, knowledge of this event, how does that spread? Okay. Well, we think at least that time is irreversible, right? So we cannot know about this event until it has happened. Okay, so that's how we think about it, at least. But then knowledge of this event is spread in time and space according to some time-space cone like this, right? So here, event 1 is observed or observable by some observer, right? So some observer that is placed in space and time will be able to know about E1 if it's in the cone, the space-time cone. Then some other event might happen down here at some space-time coordinate given by that dot, and that propagates like this in another space-time cone. So if we have a station which is placed on these space-time coordinates, some observer, let's call it observer number 3 here, it will learn about this E1 at that time, and it will learn about let's move no. I should have rehearsed this. Some observer here. It will learn about E2 at that point in time, right? And then it will learn about E3 at that point in time. Okay, did that make sense to you? Okay. I'm not sure if it did, maybe, or if I explained it very well here. But the thing is that things happen at a certain time space coordinate, and then it's noticeable or observable at some other space time depending on these cones here. So a very simple example of this is when we have a transmitter and a receiver like this. So maybe we have station number 1 here and station number 2 here. Then if station number 1 starts to do something, maybe transmit the frame at this point in time, when is it known, or can it possibly first be detected at station number 2? Well, it depends on the distance between these two and the propagation speed of the medium over which station number 2 and station number 1 is connected. So it takes at least the propagation time before this event can be noticed at station number 2. So again, an event at station number 1 occurs at some point in time, and then the event is observed by station 2 at some other time. And the quickest station number 2 can learn about this is given by the propagation time. Okay? And the propagation time depends on the distance, the physical distance these two devices are separated with, and the propagation speed of the medium that connects these two stations. All right. So now, suppose we have then two stations here, 1 and 2. They want to communicate with each other. They want to exchange frames. And they are not synchronized. There is no time synchronization between these two. They just get frames from their upper layers and they want to deliver that to the other end. And they're using the following rules. That a station with a frame to send listens to the medium first to see whether there is an ongoing transmission. If there is an ongoing transmission, it waits. The station then monitors the medium. Okay, and then it listens to the medium, and then when the medium is found to be idle, so there is no signal ongoing on the channel, it starts to transmit its frame. And then it listens to the medium to detect a collision. And if a collision occurs, then the station that began to transmit earlier retransmits, and the propagation time is assumed to be known. And after transmission, the winning station is silent for a certain period of time for the other station to capture the channel. Okay, so these are the rules, and let me now explain them, right, in a diagram. So, oops. Yeah. Let's go here. So I'll skip that slide and go back to it later on. Sorry. Okay, so we have station 1, now it's called station A, I'm sorry for that. So A and B, they want to communicate. So A here listens to the channel, it has a frame to transmit, and listens to the channel at this point and say, okay, it's empty. So now I start to transmit my frame. And it starts to send the first bit, second bit, and so forth, and keeps on going like that. At the same time, station B is listening to the channel, and at this point in time, it receives a frame from the layer above it. And since the channel is assumed to be free at this point in time, because it hasn't heard anything, right? Okay, station number A has already started to transmit, but this is not known to station B at this point in time. So station B thinks that everything is clear, and then starts to transmit its frame. Okay. So now we have problems here. We have a collision ongoing on the medium here with 2 transmissions at the same time. Now, station B at this point in time realizes, there is an incoming frame here. And it knows that this frame must have been started to be transmitted before I transmitted, because I know the time it takes to go from here to here. So if the time difference between transmission start and detection of a collision is less than the propagation time, I know I was last onto the channel. Okay? Let me do that again because it's important. So station B here listens to the channel and says, everything is clear. I start to transmit my frame. And then a little bit later it says, there's something else ongoing. Now I need to decide whether I have priority or not. Okay? And the rules are the first one on the channel wins. Then if this time here is less than the propagation time, then I know I was last onto the channel, and therefore I should back off. Okay? So if I'm station B, I stop transmitting at this point in time. Station A then is happily transmitting its frame here until here it notices, there is another ongoing transmission here. But it knows that the time before from initiating the transmission until it realizes that something else is ongoing is more than the propagation time. Then station A knows I'm the winner. So I can continue. So station A just simply continues. And then when the frame is done, it stops to transmit. Okay? What happens at station B? Well, it starts now to receive the blue frame until this point in time. At this point in time, station B here knew it was the loser at this point in time. Station A knew it was the winner at this point in time, for sure. Okay. So at this point in time, everything is clear. A and B knows what's going on. B knows that A is transmitting. A knows that B started to transmit, but it also knows by the rule of the protocol it stopped transmitting. So now the channel is captured by station A. So this initial part here is basically only to coordinate. Okay? So this blue part here is coordination information. It carries no data from the layer above it. Right? It's just probing signals in order to figure out who has priority of the channel. Then the actual data comes. So we just finished the coordination period, and now the data transmission period starts. And it continues for a certain amount of time, depending on how much data there is to be transmitted and also the data rate. And then it finishes here, and then it takes a t-prop seconds before it arrives finally at node B, station B. Okay. And then we're back into a situation where we are here already. The channel is now idle, and the process can be repeated. That one fights for priority of the channel, and then the winner transmits its frame, and then there's a propagation time that one has to wait before the actual transmission has been completed at the other end. Okay. Any questions on the logic here? So we basically have three phases here. The propagation, the coordination phase, part 1, the data transmission phase, and then the coordination phase at part 2 here. Okay, and the coordination phase at part 2 here is that even though that the channel is idle at this point in time, station A is not allowed to transmit immediately here. And why is that? Yes? Exactly, then one would kill station B. Station B would never be able to transmit until station A has ceased to transmit, right? So to have some fairness here, one gives station B a chance to, you know, chime in. And typically, maybe this propagation time could be a little bit, okay, this is a toy example, so it's not going to work in reality, but that's the main principle, right? One has to also enforce a little bit of fairness here. Okay, so now, is this a good scheme or not? Well, let's go back to the earlier slide and then say something about what would be performance metrics for a medium access scheme. Well, one thing that matters is the time it takes to transmit the frame. Okay, and then it means from the time that the service data unit arrives from the layer above it until it's been delivered to the receiving MAC at the upper layer. So when it comes from here at a certain time, what time it takes before it's pushed up at the other end. Throughput is another thing, which is the actual transfer rate through the shared medium. Okay. And that's in frame per second or bit per second. Now, suppose here we have a number of nodes using the shared medium. So maybe we have station number 1, station number 2, and so on. And at the end, we have station number M. All of them are connected to a shared medium of some sort. Okay, so the medium needs to be shared here. The medium here has a capacity of R bit per second. So that's the maximum transfer rate we can have on that channel. And that R bits per second needs to be shared among the different stations here. Suppose then that station number 1 transmits frames at a frame rate of lambda 1. So lambda 1 is the number of frames per second generated by station number 1. So in general, lambda m is the number of frames generated by station station M per second. Now, suppose that L is the number of bits per frame. Then the mth node is generating a data rate that is lambda m times L. So lambda m times L is the bits per second generated by station M. Okay. So capital L here is the number of bit per frame, and this is what we used to call in ARQ NF. Okay. So we have changed notation here, and the reason for that is I want to be consistent with the book that changes notation between two chapters. Okay. So L here is the number of bits in a frame. Okay, so then the total rate generated by all nodes attached to this medium is the sum of the rates, right? So if we sum the rates from m equals 1 to capital M of all the individual rates, we get the overall rate, which is also known as the aggregated rate or the total rate. So this is known as the aggregated frame rate or the total frame rate. It's the sum of all the station rates. And then the total number of bits per second which is generated is lambda times L, is the bit per second generated by all stations. Okay. Then we can define what we call the load. Okay. So the load, or channel load, sometimes called channel load, is how close we are to the capacity of the medium. So the capacity of the medium is R, and the aggregated rate, bit rate of the channel, which is generated by all the stations, is this lambda times L. These are the total number of bits per second generated by all the stations. Now, if there is not a whole lot of data, the load will be low. If it's a lot of data, the load will be high. So the load, rho, is the ratio between the generated rate and the maximum rate that the medium can handle. So the total rate is lambda times L, and the total capacity of the channel is R. Okay. Okay. So once more, we have a number of stations, m of those. Each of them are generating some data traffic. And lambdas is in frames per second, and lambda times L is in bit per second. The total number of frames that are generated by all the nodes is lambda. It's the sum of the rates, the individual rates, and the total number of bits per second which is generated is the number of frames per second multiplied with the number of bits per frame. Okay. So we have here some traffic which is generated by all the stations, and that divided by the total capacity of the medium tells us what the load is. Okay, so for this to work, the load needs to be less than 1 or equal to 1. You agree? I mean, if this is a 1 megabit transmission line, and some station here together generates 2 gigabits per second, things will not work, right? So when we're in an overloaded situation, there is no hope we can share the medium, right? Something bad is going to happen. But if rho is less than 1, at least we have a shot at it. Okay? There is a chance if we do the medium access control efficiently. That is, we have good coordination between the transmitters. Questions? Is it clear somewhat? Okay. So this load here is basically how much we stress the system. Now, a medium access control scheme, a practical one, can support a rate or a load. Should maybe normalized is the wrong word here, but the load here has to be somewhere less than some rho max, which is less than 1. Okay, just to take into account the fact that in order to coordinate the stations here, we need to communicate over this medium, and that takes away some of the effective rate that we can support for useful data. Okay, the transfer delay typically increases, so the transfer delay here typically increases as we push the system closer to its maximum capability. Okay, so now when we know this, let's calculate the performance metrics for this particular system. It was super simple. I only had 2 nodes and then a simple protocol like this. No errors, nothing like that. So what is the effective rate we can generate of this? Well, it has to do, as we did previously, it's the number of useful bits divided by the time it takes to transmit those bits. Okay. How about this? Let's take a break and we do the analysis after the break. Ja, en röd knapp.